At first glance, the moon's surface appears calm, motionless, and at peace with its past. But beneath that calmness lies a discovery that has stunned the scientific world. In 2019, astrophysicist Peter B. James from Baylor University was analyzing data from the Grail mission when he identified an unusual mass near the moon's south pole. This wasn't just a density anomaly. It was a massive structure hidden beneath the surface, large enough to noticeably affect the moon's gravity. According to scientists, this mysterious mass has a volume roughly 5 times that of the island of Hawaii, and it isn't made of ordinary material. Simulations suggest that to cause a gravitational anomaly on this scale, the structure must contain heavy metals like iron or nickel. What's more, this colossal object isn't sitting on the crater's surface, it's buried deep below. It rests wedged just beneath the moon's outer crust. One possible explanation is that about 4.5 billion years ago, a massive asteroid struck the moon, and its metallic core is still buried under the surface. The impact was so powerful that it shattered the moon's outer crust, carved out a crater deep into the mantle, and brought subsurface materials to the surface. If this theory is correct, what we're looking at may not just be part of the moon, but a remnant of an entirely different celestial body. The presence of heavy elements like nickel and iron suggests this isn't an ordinary impact site. It's not only massive, it's also unique in terms of what it contains. But how was this structure detected, despite being buried miles beneath the surface? The Grail mission relied on a surprisingly simple principle. 2 identical spacecraft orbit the moon, flying one behind the other. Even the slightest variation in the distance between them reveals differences in gravity caused by mass changes below. It's like detecting an invisible mountain by observing subtle shifts in the terrain around it. Except this time, the mountain isn't on the surface. It's hidden 300 kilometers deep. The region where this massive metallic structure lies is no random location. It sits right at the center of a colossal impact crater known as the South Pole Aitken Basin. This basin isn't just the largest on the moon. It's one of the biggest and deepest known impact structures in the entire solar system. Spanning about 1,550 miles wide and reaching depths of 5 miles, it forms a vast depression that covers nearly the entire southern hemisphere of the moon. That size accounts for roughly a quarter of the moon's surface. One of the most intriguing aspects of the South Pole Aitken Basin is that we still don't fully understand it. No human or robotic mission has ever landed there. Everything we know comes from orbital data. That means we have no close-up photos from the ground, no geological samples either. And yet, radar and gravity measurements clearly show that this region is key to understanding the moon's history and may hold strategic value for future missions. The massive impact that formed the basin also created an area of permanent darkness, where even light cannot reach. That's because the collision occurred very close to the moon's south pole, and the poles of the moon behave very differently from those on Earth. The reason lies in the moon's axial tilt, which is almost non-existent, just 1.5 degrees. In other words, the moon spins like a nearly upright ball. As a result, certain craters near the poles never receive direct sunlight. Scientists refer to these regions as permanently shadowed craters. The term doesn't describe temporary darkness, but rather an unbroken shadow that has lasted for millions or even billions of years. Sunlight can reach the edges of these craters, but their floors, the deepest parts, have remained in total darkness since they first formed. At first, this was only a theoretical idea, but over the past 15 years, especially thanks to NASA's Lunar Reconnaissance Orbiter mission, scientists have been able to map these permanently shadowed regions in detail. Instruments like LEND and Diviner, onboard LRO, scan the moon's surface thermally. The temperature data revealed that the floors of some of these craters can reach negative 382 degrees Fahrenheit. Such extreme cold isn't just rare on the Earth-Moon, it's rare anywhere in the solar system. These temperatures are usually found far beyond Neptune. This kind of pitch black and freezing environment means something very specific to scientists, because conditions like these create the perfect environment for preserving a substance over incredibly long periods of time. That substance isn't a liquid, but a solid form of a key ingredient for life: water ice. If water can survive inside these frozen craters, the moon's most valuable resource might have been hiding there for millions of years, just waiting to be found. And that would be more than just a scientific discovery. It could change the course of future human exploration. The core idea behind this possibility is something scientists call a cold trap. It refers to the way volatile substances, especially water molecules, can accumulate in ultra-cold areas on the moon. Micrometeorite impacts, solar wind hydrogen ions, or even ancient volcanic activity might deliver water molecules to the surface. But if one of those molecules lands inside a crater that never sees sunlight, it may never leave. Trapped by the cold, the molecules eventually settle into a thin layer of ice on the surface. Scientists believe that the moon's poles may contain hundreds of these so-called cold traps. Some of them are more than 6 miles wide. Each one is like a small, isolated archive, shielded from external influences, and it's not just water that might be hiding there. Other volatile substances like carbon dioxide, ammonia, and more could also be preserved in these frozen pockets. But there's another factor that strengthens the case for water ice: asteroid and comet impacts. Some of the objects that struck the moon in the past are thought to have contained water. If one of these impacts happened near a permanently shadowed region, the released water molecules might have briefly lingered on the surface, then migrated into colder areas where they could settle and freeze. This process could have repeated itself slowly over millions of years. So while the moon may appear dry on the outside, its surface might actually be dotted with frozen reservoirs hidden in plain sight. But to move beyond speculation, direct evidence was needed. The hypothesis was strong, but it remained unproven. So what would happen if something collided with the darkness? Because sometimes the only way to find out what's hiding in the shadows is to disturb them. That's why scientists decided to deliberately strike a permanently shadowed crater near the moon's south pole. Launched in 2009, the El-Cros mission was designed to put this idea to the test, and it would become a turning point in lunar research history. The mission plan was bold. First, the Centaur rocket was directed to crash into the Cabeus crater at over 5,600 miles per hour. Just a few minutes later, the El-Cros spacecraft followed, flying through the plume of material kicked up by the impact, analyzing it in real time. What they saw wasn't just dust. A reddish cloud of gas and particles rose miles above the lunar surface, and El-Cros's onboard spectrometers began scanning that cloud within seconds. The data they collected included some of the strongest signals of water ever recorded on the moon. Traces of water vapor, hydroxyl radicals, carbon dioxide, ammonia, and even some organic compounds were detected. This didn't just confirm the presence of water, it showed that it was chemically bound with other substances as well. These compounds appear to remain stable within the permanent shadows, where temperatures can drop to nearly negative 400 degrees Fahrenheit. Around the same time, India's Chandrayaan-1 spacecraft also achieved a similar breakthrough. Using spectroscopic data, it indirectly confirmed the presence of water molecules on the lunar surface. These spectral signatures were especially prominent in regions experiencing sunrise and sunset. By this point, the scientific community was growing more confident. Yes, water existed on the moon. At the very least, traces of it had formed in the past and remained locked away in these frozen shadows. But this led to a new question. If water is really there, why can't we see it directly? In 2023, India's Chandrayaan-3 mission successfully landed near the moon's south pole. The Vikram lander and its small rover, Pragyan, were now in the most important region in lunar science, ready to analyze the surface up close. The objective was clear. If water was hiding in the permanent shadows, perhaps traces of it could also be found just beneath the surface. In the days following the landing, Pragyan focused on scanning shadowed slopes nearby. It carried advanced instruments like the alpha particle X-ray spectrometer and the laser-induced breakdown spectroscope, both designed to analyze the chemical composition of the surface. And one of the most surprising results was the absence of hydrogen. In other words, hydrogen, the essential building block of water, couldn't be detected as expected. This seemed to contradict earlier spectral data because missions like El-Cros and Chandrayaan-1 had strongly confirmed the presence of water or hydroxyl groups. This contradiction led scientists to consider two possibilities. The first, perhaps water didn't remain near the surface and had slowly migrated deeper underground over time. The second, maybe the earlier missions had only detected brief surface-level reactions, meaning water might never have actually existed in a stable form. But there was also a third explanation. Maybe the issue wasn't where we were looking, but how we were looking. Maybe traces of hydrogen were still there, but we lacked an instrument sensitive enough to detect them. That's why this time, instead of simply looking into the shadows, scientists decided to observe them from an entirely new perspective. Waiting for sunlight was not an option, because the region being studied was one of the moon's permanently shadowed areas. Sunlight never reaches those parts, and traditional cameras can't capture any visible detail in such complete darkness. To solve this, scientists developed a new approach: seeing the shadow directly. One of the most advanced systems designed for this purpose was ShadowCam. In 2022, NASA and South Korea's space agency KARI launched the Danuri spacecraft to the moon. On board was ShadowCam, an instrument capable of detecting not just light, but even the faintest glimmers within complete darkness. It was 200 times more sensitive than a normal camera. This allowed it to peer into shadows using nothing more than faint reflections of indirect sunlight. ShadowCam scanned deep craters near the moon's south pole, such as Shackleton, Faustini, and Haworth, in remarkable detail. For the first time, images revealed the interior of the permanent darkness. But the results didn't match expectations. There were no clear signs of ice crystals. Still, the camera didn't just document absence, it also captured details about surface depressions, slopes, and reflection patterns, offering clues about the region's electromagnetic environment. Because inside these shadows, it's not just dark. These are also quiet zones where charged particles accumulate. The silence observed in ShadowCam's images raise an important scientific question. If ice isn't visible, but the surface still appears active, what does that suggest? The answer might lie in the very nature of the surface material. The regolith at the moon's south pole, the loose mix of dust and rock covering the ground, isn't just a passive residue. On the contrary, these fine particles are constantly bombarded by solar wind and cosmic rays, causing them to accumulate high levels of electrical charge. In permanently shadowed areas, this effect becomes even more pronounced. Since sunlight never reaches these zones, ionized particles are more likely to settle and build up over time. As a result, an invisible but hazardous phenomenon can emerge on the lunar surface: electrostatic traps. These traps pose a serious risk, especially for spacecraft landings. The electrically charged regolith particles can generate strong voltage differentials that could damage landing systems. And the danger doesn't end there. Once stirred up by engine thrust during descent, the particles can cling to electronic components and optical instruments. NASA's Lunar Atmosphere and Dust Environment Explorer had already observed that these microscopic dust particles form a cloud around the moon. It's believed that in electromagnetically isolated regions, like the South Pole, such accumulations are even more concentrated. So even without visible ice, these areas remain active and dynamic. This part of the moon, though hazardous, also offers unique opportunities. That's because certain resources may only exist here, and that fact could signal the beginning of a much larger race. The lunar South Pole is not just dark, it's dangerous. Yet despite all these challenges, this region has become the primary target of nearly every moon mission in recent years. Not just for scientific exploration, but also for the dream of permanent settlement. But why? Why is all attention focused on a place where the surface is unstable, the soil is electrically charged, and the presence of water is still uncertain? The answer lies in three critical resources: water, sunlight, and strategic location. First, the possible presence of ice within the permanently shadowed areas could mean access to both oxygen and drinking water for future lunar bases. The same water could be split via electrolysis to produce rocket fuel. That would turn the South Pole into a fueling station, not just for the moon, but for future missions to Mars and beyond. The second reason lies just next to those frozen craters, ridges that receive nearly continuous sunlight. Because the moon's axial tilt is very low, some high points near the poles remain sunlit for most of the year. This makes them ideal for operating solar-powered systems without interruption. In particular, the area around Shackleton crater holds a uniquely favorable position for this. The third reason is geopolitical. The moon's south pole may hold unique mineral resources that could play a pivotal role in the future of space-based economies. That's because the geology of this region has been explored far less than other parts of the moon, making it not only a land of unknowns, but also of extraordinary potential. While the United States plans to send astronauts here through the Artemis program, China is aiming to build a permanent station in the same region via its Chang'e missions. Countries like Russia, India, and Japan have also joined the race with missions of their own. All signs suggest that the lunar South Pole could become not just the heart of the moon, but the center of the entire space age. But it's not only about accessible resources. Some materials exist exclusively in this region, and the true wealth may lie deep beneath the surface. In certain parts of the lunar soil, particularly near the South Pole, scientists have detected an isotope that is almost non-existent on Earth, helium-3. This element could serve as an ideal fuel for nuclear fusion reactors. Unlike thorium or uranium, it is non-radioactive, so it doesn't produce high levels of radioactive waste. And the amount of energy it releases during fusion is remarkably high relative to its mass. But how did helium-3 accumulate on the Moon? The answer comes directly from the Sun. Solar winds continuously eject charged particles into space, including helium-3 ions. Earth's magnetic field blocks these particles, but the Moon has no such protective shield. As a result, helium-3 has been directly embedded into the lunar soil over billions of years. The regolith in the polar regions, in particular, can trap and preserve these particles for an exceptionally long time. According to current estimates, the Moon's surface contains millions of tons of helium-3, and even a small fraction of that amount could meet the annual energy needs of millions of people on Earth. But unlocking this potential is far from easy. That's because helium-3 is buried just a few microns beneath the lunar surface. To extract it, the regolith must first be mined and then subjected to special thermal processes to separate the gas. That means advanced technology, a continuous energy supply, and permanent infrastructure on the Moon. And that's precisely why helium-3 is not just a source of energy, it's a geopolitical card being played for the Moon's future. Whoever manages to extract it will gain more than energy, they'll have a stake in the future space economy as well. But even with all this potential for energy and water, one question still remains. Can we truly establish a permanent human presence on the Moon? Let us know what you think in the comments, and we'll see you in the next video.